Hi everyone, welcome back to your next set of notes. We are covering solving exponential and logarithmic equations in this section. It is the last section, like I said, and we're going to kind of incorporate everything that we've learned about exponentials and logs, being able to convert in between them, as well as properties of exponentials and logarithms in order to isolate our variables. And the reason why it's important is because there are a lot of real-world applications. We talked about them a little bit on day one of exponential and logarithmic models in medicine, in science, the Richter scale that measures the intensity of earthquakes is a logarithmic scale. Half-life, the spread of infectious diseases like coronavirus is an exponential function. And so we're going to solve an equation and apply it to different word problems as well in this section. So there's a lot. So the first thing that we need to do is to keep in mind our properties for exponentials and logarithms, as well as always keeping in mind that we want to isolate our exponential or logarithm or get them to match. Those are kind of our two goals. We either want let me just dismiss that. We either want the two sides to match in terms of bases, or we want to isolate an exponential or a logarithm in order to solve it. So let's take a look here. So I've tried to color code this so that you can see which property I'm applying, but we have a very simple exponential equation, 2 to the x equals 32. So they're asking us, what would we raise 2 to the power of to equal 32? Well, we can see it really easily if we write 32 as a power with a base of 2, and 32 is 2 to the 5th power, and if our bases match, exactly, we call that a one-to-one property. Well, then obviously the exponents need to match as well. We can do the same thing with a logarithm. So here I have log of base 4 of x minus log base 4 of 8 equals 0. But if I just add to move my log base 4 of 8 to the other side, I have a matching base. So again, it's just a one-to-one property with a logarithm. And so as long as the bases match, then the two terms need to match as well. So those are the simplest kind of exponential and logarithmic equations. Here we have another example of a one-to-one. It's just like B, except we use a natural log, but it's the same thing. A natural log is just a regular logarithm with an assumed base of e. So in letter D, you could think of this a couple of different ways. So this is, I've applied, if you take a look up here, a one-to-one property, where if we need to, or I'm sorry, not a one-to-one, an inverse property, where if we're given an exponential and we can't convert it to have matching bases, and actually this one we could, but the simpler way might be to just use an inverse property. So what I'm doing is I'm trying to undo my base of 1/3. So I'm going to take the logarithm of the base of 1/3, which gives me log base 1/3 of 1/3 to the x power. Those inverse properties, they cancel each other out, or they undo each other, which leaves me just with my variable on this side. But what I do to one side, I have to do to the other. So that's why I took the log of base 1/3 on the other side as well. And this is something you can put in your calculator. Remember, if you use a Casio, you just need to use the change of base formula. Or if you use a Desmos on your phones or something like that, you can just plug in whatever base you need. I could also think of this as, I could rewrite it with a base of 3. So this would be 3 to the negative 1 power. So it would become 3 to the negative x power, and 9 is 3 to the 2nd power. So I would have matching bases again in that case, and I could use that as well. So that might be easier for you to think of, but you have to remember that a negative exponent takes the reciprocal of your base. In letter E, again, we have an inverse property at work where we took the natural log because we have a base of E of both sides. So then that ended up canceling out our base. And then this, again, is something that we can plug into our calculator. And same thing here, except it's a natural log equation starting out instead of an exponential equation. But we do the same thing. And then with G and H, again, same types of examples. Okay, so what I want to talk about is sometimes it's a little bit cumbersome to apply an inverse property, but another way that we can think about an inverse property is to convert whatever type of equation we're giving, whether it's a logarithmic or an exponential equation, to its other form. So in letter A, we're given an exponential equation e to the x equals 72. So I can convert this into a logarithmic equation instead of taking the natural log of both sides. So all I'm doing is rewriting this as the other form of the equation because they are inverses of each other. They solve each other, they cancel each other out. So a logarithmic will isolate the variable for you of an exponential equation, and vice versa, an exponential will isolate a logarithmic variable for you. So then you get directly to the x equals natural log of 72, and you can just plug that into the calculator and round it. We're doing the same thing here, but if your logarithmic or exponential term is not isolated, that's always going to be the first thing you do. So we need to isolate this 2 to the x by dividing by 3 on both sides, and then I can convert it into a logarithm, and then plug that into my calculator. Okay, again here, I just need to isolate my exponential. I divide by 4 on both sides, then I convert it into a logarithm, and then plug this into my calculator. So ln of 1/2 became this negative 0.69315, and then I added 3 to both sides and then divided by 2, so I solved for my x. So the key is to isolate first whatever your exponential or logarithmic term is. So in this case, there are 2 things that I need to do. I need to add 4 to both sides and divide by 2. And then I converted this from an exponential into a logarithm. And then I plugged log base 3 of 15/2 into my calculator, and I got this. And then I solved for t by adding 5 and dividing by 2. So now what we're doing is, oops, I'm too far down. Is we are focusing just on logarithmic equations here, but it's really the same thing. We're converting from a logarithm to an exponential and then solving. I am not sure why I didn't finish this one, but to solve for x, once I've converted it into an exponential, I just divide by 3 on both sides. So I would get for a final answer, if I don't want a rounded answer, then just don't plug it into your calculator. Just simplify, isolate your variable, and then leave the answer as you see it. So, for example, in letter A, you would get x equals e squared over 3. So that is something that you could plug into your calculator and round, but if the problem asks you for an exact answer, not a rounded answer, then just leave it as e squared over 3. This is, if we look at, we don't have to convert. It's a 1-to-1 property. We have matching logarithms on both sides, so I can just drop them and then set those to what I'm taking the log of equal to each other and then solve that equation. So that one's pretty simple. In this case, I have to isolate my natural log first. Remember, that's always the first thing that you do when you solve either of these equations. So we subtract 5 and divide by 2, which gives me natural log of x equals negative 1/2. I convert that into an exponential. Again, in this case, I don't want a rounded answer, so I leave it as e to the negative 1/2 power. And then finally in D, I am dividing by 2 on both sides to isolate my logarithm. I convert it then into an exponential and then solve for my variable. Okay, and then the last thing we need to focus on, specifically with logarithmic equations that we haven't had to do before, you don't have to do this for exponentials, but for logarithms, you always have to check for extraneous solutions. If you remember the graphs of logarithms, they always have vertical asymptotes, meaning that there is an imaginary line that the graph doesn't cross, or in other words, there is a restriction on the domain. There are some values for x that will make the equation not work. And those are if you're taking the natural log or the logarithm of anything negative. You can't do that because there is no exponent that makes a number negative. Negative exponents, remember, just make the reciprocal, which is why the graph of, y equals log x or y equals ln x, it doesn't go past the x-axis. It stays every x value that's greater than 0. So we always need to make sure that when we solve a log equation, we check for any extraneous solutions. So if we take a look here, the first thing I'm doing is I'm applying a product rule to condense my log on the left side into a single expression. So I have x minus 2 times 2x minus 3, which when I multiply out becomes 2x squared minus 7x plus 6. Once I've done that, I can come over here on this left side, and I don't need to condense anything using product rule, but I do have a coefficient in front that if I divide it on both sides doesn't help me because I just end up having a coefficient on the other side. So what I do is I'm going to apply the power rule, and a coefficient of a logarithm becomes an exponent. So then now I have matching logs on both sides, so I can drop my natural logs and then just solve the resulting equation. It is a quadratic equation, but when I get everything over to one side, it factors really easily, and it gives me 2 possible solutions. But if I double check those by plugging them back in one at a time, so first the 6 works no problem. I get ln of 6 minus 2 plus ln of 2 times 6 minus 3. ln 4 plus ln 9, if I condense that using product rule, I get ln 36. And if I condense over here using power rule, I get ln 36. It works. Both sides match. But on this side, when I plug in 1, I end up with a negative number that I'm taking the natural log of in both of these cases, and that makes this undefined. You cannot take the natural log or the logarithm of a negative number. There is no value for that because a log is answering the question, what exponent makes me get a negative number? In this case, -1, and there is no exponent that will do that. So there is no x value. So that's why this is undefined and why we get an extraneous solution. So our only solution in this case would be x equals 6. Okay, so we're running out of time here because I don't want the video to go above 15 minutes. But we're going back to word problems. In example 5, it's a compound interest problem, which we did a lot of practice on, I think all the way back in day 1. So we're applying our PERT formula because it's a continuously compounded interest, and we're just plugging in values from the problem. Our principal amount is 500. That's the amount we're starting with. Our rate is 6.75 or 0.0675 as a decimal, and we're trying to end with double the money or $1,000. When I plug that in, I'm solving for t, or the length of time it will take for my money to double. And I'm going to solve this just the way I've solved all the other ones. I'm going to isolate my exponential. So I'm going to divide by 500 on both sides, and then I'm going to convert it into a logarithm. Once I do that, then I can plug things into my calculator. So ln2 became 0.69315, and I just need to now solve for my t by dividing on both sides. So I get roughly 10¼ years. And then the last problem is pretty self-explanatory. We are modeling teacher salaries using this logarithmic equation. And I'm just plugging in to find out what year or what t value average teacher salary became 45,000. So my y is 45, and then I just need to isolate my logarithm. So I'm adding this and dividing by this, which gives me ln t. And then I convert that into